let's start to get some practice using integration by parts to evaluate certain integrals. Again, like in the u substitution example video, I'm only going to focus on indefinite integrals. And that's, again, just to get the practice focusing on the technique. So first example, if we had to find the antiderivative of the natural log of x, a very common mistake here is that I will see a student write that this is equal to 1 over x, which is, of course, the derivative. We want to go in the other direction. So one thing that makes this a little complex is we've specified the idea that in integration by parts, we're used to looking for a product so that we can identify u times the derivative of v. And of course, this doesn't look like a product, but any function, we can force it to be a product of that function and 1. So as we start to get more techniques, it will be clear that when you encounter an example like this, that none of the other techniques apply. So this is kind of a last resort that we could think, well, what if I force it to be written as a product? So now I have two functions, and we talked about getting the practice of finding u and finding dv. Sorry, that should be dv. This is a classic example where the second point I made about how to come up with these functions is valid. So in that point, I mentioned that you have to choose dv so that you can actually antidifferentiate it. If I were to put natural log of x in for dv, I'm right back at the beginning of this question because I am, in fact, trying to figure out what the antiderivative is. So I really have to choose u to be ln of x, in which case dv is just that 1 dx. Now the derivative of ln of x is 1 over x dx. The antiderivative of 1, I can write here as just x. So now, again, I multiply u times v, so in this case x ln of x, minus the integral of v du. Of course, in this case, this simplifies to just 1. So I get x ln of x minus x, but I have to put in that, again, the plus c for this indefinite integral. So now we see that sometimes we might try to look for writing a function as a product of itself and 1. So we've seen some examples of just integrating familiar trig functions. Turns out that for certain inverse trig functions, integration by parts can be useful. I'll point out that this arctangent of x is equivalent if you're used to writing tan inverse, so tan with the -1 up top. I prefer this notation. I don't care which you use, but the reason I prefer this notation is a lot of times I see people mistakenly think of this as 1 over tangent, and it's not that. This is the inverse function of tangent, so just to be careful with that. Again, u substitution would not help me here, and so the only other technique we have so far is integration by parts. We've just seen an example where we might want to view the integrand as a product of itself and 1. So let's use that again. I'll point out the same problem that we had before is that I don't know the antiderivative of arctangent. So if I'm trying to solve that, I really have to choose my dv to be 1 and not arctangent because I couldn't antidifferentiate. So the derivative of arctangent, recall, is 1 over 1 plus x squared. And again, we get the antiderivative of 1 is x here. So now I can take u times v minus the integral of v du, which that yields x over 1 plus x squared. Now, I have that integral. It's a very different integral from what I started with, but it's also not one that I can just immediately look at and think of the antiderivative. But now let's pause and think about what we would do with this integral. This would be a classic case to use u substitution. And of course, it's unfortunate that the letter u is playing many roles here, but I'll kind of scratch off this. We're done with this part. So I want to figure out what to do with this integral. Well, I'm going to let u equal x squared, in which case du is 2x dx. And therefore, 1/2 du can replace the x dx. So I'm carrying through the x arctan x. But now I'm going to write this as minus 1/2 the integral of 1 over u. Sorry, I should choose u to be 1 plus x squared. I'd have to make another u substitution. So putting in the 1 plus x squared, it doesn't change my derivative du. So putting this in here, I get 1 over u du. Now I can anti-differentiate that to get the natural log. So this becomes x arctangent of x minus 1/2 natural log of absolute value of u plus my integration constant. So I want to substitute back in what u is in terms of x. And after I corrected that, it was 1 plus x squared. And I have this plus c. Now, of course, this is a suitable way to write it. In this instance, you could lose the absolute values because 1 plus x squared is always positive, but this is fine as well. So what we're learning from that example is sometimes I can start with integration by parts, and then I might need to use u substitution to solve the new integral I introduce. If we have the integral of x squared e to the x, this is more recognizable as a product. If I learn from what we saw in our first example in the last video, our only example, I suppose, this is one where we can anti-differentiate both x squared and e to the x. However, when we talked about the other point of trying to choose u so that du was in some ways simpler, it turned out that power functions are nice in that way because you're reducing that power when you take the derivative. So we rewrite this. I have x squared e to the x minus the integral of v du. So I have 2x e to the x. Notice that this integral that I've introduced, one could argue that that's simpler than the one on the left, but it's still not obvious. And so what we're seeing here is that I can use integration by parts yet again. So making a different assignment of u and dv. So on this integral, I could let u once again be the power function, 2x in this case. Derivative is 2. dv is e to the x dx, and therefore v is e to the x. So now I'm going to use this second round of integration by parts to rewrite this. And one thing that you really want to be careful with is making sure that you distribute. So I have a minus sign there, and I need to distribute that throughout. So kind of recognizing that I'm replacing that boxed expression when I use integration by parts here. So we're going to get what we already had out front, x squared e to the x, minus, and I'm going to put parentheses here, u times v in this instance is 2x e to the x, minus the integral of v du is 2 e to the x. So we get x squared e to the x minus 2x e to the x. And notice I have minus a negative, so plus the antiderivative of 2e to the x is 2e to the x. And then we have our additive constant c. So the last example, we saw integration by parts followed by u substitution. And here we saw integration by parts followed by another application of integration by parts. So you can use that several times in a row if necessary. So the next example, e to the x cosine x. So we're going to see a strange thing that happens in the process of solving this that is representative of using integration by parts on what we could say functions that are somewhat cyclical, that you end up back with either the function itself or something related to it when you take derivatives. So you really could choose here u or dv to be e to the x. Turns out it doesn't matter as long as we're consistent. So I'm going to choose u to be cosine of x. If you made the choice to let u be e to the x, this would work as well. So du is then minus sine of x dx. V is e to the x. So I can rewrite the original integral as e to the x cosine x minus a negative, so plus the integral of e to the x sine of x. So now I have another product, and it doesn't look terribly promising in terms of what we started with and now what we have, but it certainly is a product, and I could use integration by parts again. So ignore the assignment of u and dv from before. What I was talking about being consistent here, I chose the trig function to be u in my first step, so I'm going to do that as well. So you let u be sine of x, in which case du is now cosine of x. And I'm going to let dv then be e to the x dx, like before, and v is e to the x. So what this gives us is the integral that we started with, whoops, that of e to the x cosine x. I'm saying that's equal to e to the x cosine x, which is what we got after our first integration by parts, plus what we're going to get now. So again, what I've done on the second part is figured out how to rewrite this. So this is going to yield e to the x sine x minus the integral of e to the x cosine x. Based off of what we've done so far, this does not seem good because I end up where I started with more stuff in some sense. So this integral, notice, is the same as that on the left. But it turns out that that's okay, because you can view this as an algebra problem. We have the unknown, which is what we have on the left, that we're trying to solve for. But it shows up on the right-hand side as well. So what I want to do is isolate that unknown, and I can do that by adding the one on the right over to the left-hand side. So notice that that implies that twice the integral we're trying to evaluate is now equal to e to the x cosine x plus e to the x sine x. So I can simply divide both sides by 2 to isolate this. Now, one thing that can be overlooked in this technique is we're looking for an indefinite integral. So somewhere I do want to put in my additive constant. So I'll do that in the last step. So we have 1/2 e to the x times the quantity cosine x plus sine x plus some additive constant. So we see there that if you end up with what you started with, not necessarily a bad thing if you can rewrite that expression to allow you to still solve for that integral. And then finally, I want to end with an example that we saw for u substitution so that we, oops, I guess this is number 5, so that we can compare the techniques for solving the same thing. And this is the integral of sine squared. When we did u substitution, we had to use an identity, a trig identity to solve it. So what I'm going to take advantage of here is that this is naturally a product of sine of x times sine of x. So in terms of trying to find u and dv, both of them will be sine of x. So now du is positive cosine, while v is minus cosine. Rewriting then the original integral using this, we get minus sine x cosine x minus a negative, so plus the integral of cosine times cosine, so cosine squared of x. This is kind of similar to the last problem that we looked at, where I end up with this integral that is very similar to what I started with. Now, I'll point out, and you can try this yourself, a natural thing that we could do here, and what I think makes this difficult, I prefer the u substitution technique because of the very next mistake that's easy to make, is it would be completely reasonable for someone to go about using integration by parts on cosine squared. If you try that, you're going to find that you undo the work you did in the first step, and you'll basically end up with a statement that says the integral of sine squared is equal to the integral of sine squared, which is of course true, but does not help us solve for that integral. So in this instance, what I want to do is, we saw before, bringing in the integral we started with can sometimes be helpful. So we're looking for the integral of sine squared. We know that cosine squared is 1 minus sine squared of x. So we can actually say then that the integral of sine squared that we started with is minus sine x cosine x plus the integral of 1 minus the integral of sine squared. Now, let's think about what we learned from our last example. This is the integral on the left-hand side. We can add it over so that what I have here implies that twice the integral of sine squared is minus sine x cosine x plus the integral of 1, which is just x. And I can divide by 2 and add in my arbitrary constant to say then that the integral of sine squared is minus sine x cosine x plus x all over 2, and then tack on an arbitrary constant. Now, if you compare this to the same example in our U substitution video, the answer we ended up with there doesn't look exactly like this, but you can actually see that it's equivalent using another trig identity. So leaving it in either form would be fine, but we can look at another way to compare sine of 2x to that of sine of x times cosine x.